Okay, shall we start? Ready? So hopefully you had a little bit of rest from all that algebra, so now we can continue. So our biggest achievement for today is derivation of this equation. So, and that equation contains, well, let me just go through the components of this equation. So it contains bar quantity, u bar. So, and remember, u bar is the velocity profile of realistic flow which occurs between two plates. And we don't know how it actually looks. Our goal is to determine the type of profiles, the shape of this function essentially, which is physically observable. So the one which potentially can be seen in experiments. That's our goal. That's what we are trying to achieve. So we are trying to see what type of flows we can observe and which ones we can't really observe because of instabilities, various instabilities. So that's the physical question here. So, and there are two characteristics of perturbations. So perturbations are characterized by complex amplification rate sigma. Complex amplification rate sigma consists of two bits, sigma r and sigma I. Sigma r is the one which will tell us whether the perturbations grow, and if they grow, then the base flow that we choose is not going to be visible. Or if sigma r is negative, that means that perturbations decay and the shape of the base flow that we chose is visible, physically visible. We can actually hope to see that in experiments. And sigma I is there to tell us something else about perturbations. So perturbations can oscillate. If sigma I is equal to 0, then perturbations just do not oscillate. They die or they grow, and that's it. But if sigma I is not equal to 0, then they oscillate in time. And they also oscillate in space, right? Because alpha x, it's periodic function in space. So therefore we have spatial oscillations and we have temporal oscillations. When we combine two oscillations together, we will get a wave. Okay? So wave is essentially a combination of spatial oscillations and temporal oscillations. So spatial oscillations is just what happens in space, and temporal oscillations what happens at the same location. Combine the two and you will see the wave going. So that's what the physical meaning of these two parts is. On its own, sigma I represent essentially the frequency of oscillation. So, and psi is the stream function. So stream function does have a physical meaning, does have a physical interpretation. So, and constant, or if we set stream function to constant, we will see, so we will determine so-called streamline. This is the line along which fluid particles actually drift. That's what happens. So here we go. Now, from mathematical point of view, this is a differential equation. And what is the highest derivative present in this differential equation? Second, d squared, right? So how many boundary conditions do we need for second order differential equation? 2, okay? And we have them. So we have them physically. So we have boundary conditions which prescribe that flow through the plates cannot exist, right? So plates are solid, so nothing can penetrate through them. So W must be equal to 0. Yes, W velocity component, is velocity component in the Z direction, has to vanish at the boundaries. So what is W? W is given by x derivative, right? So what is the x derivative? The x derivative is given by this. See that? So therefore, what we see here that it is a stream function itself simply multiplied by a constant. So if W is to be equal to 0, it means that psi itself has to be equal to 0 at the walls. Is that clear? Right? So therefore, we add two of these boundary conditions, and I simply write them psi hat over, and we chose plus or minus 1/2 is equal to 0. So second order differential equation, we need two conditions, and that's what we have. Now, you might ask me a question. So we have second order derivative for psi, but we also second order derivative for u. Do we need anything for u as well? What do you think? No, because this equation already assumes that we know what u is. We don't need to determine that. So therefore, we'll simply substitute it in. Okay, if we have it, we just substitute it in, and whatever, if it is, for example, if u is equal to sine of z, to substitute this in, we will get minus sine of z, second derivative. So that's how it works. So we only are interested in solving for psi hat, and psi hat is determined from this equation plus boundary conditions. Here we go. Now, let me make one more observation. Where in this equation do we see the highest derivative of function psi? So a function psi that is the function that we are looking for. Where is it? Well, clearly that is here, right? And it is not, does not appear on its own. It is multiplied by this quantity. And what do you think will happen if this quantity happens to be 0? So if this quantity happens to be 0, well, it's clear what happens, right? So this whole thing becomes 0, right? If this whole thing is equal to 0, then we will get this expression. And this expression tells me that the product of psi and second derivative of u must be equal to 0. So which means one of them has to be 0. At least one of them has to be 0. So psi, if it is 0, well, it's a trivial solution, right? It means that perturbations do not exist. We only have base flow. So clearly this is not what we are looking for. So therefore, we will only be able to require that second derivative of u is equal to 0. And what does it mean? So if second derivative of u is equal to 0, what does that mean? So what sort of distribution is that? Second derivative is a curvature. Curvature is 0. What is that? It's just a straight line, right? So it is just a straight line profile. It might not be at 0 angle, so it might be at some angle, but it is a straight line. Okay, so that's something we will keep in mind. But the question is still, can this be equal to 0? And if you look at this carefully, you might be able to give me the answer right now without any further discussion. So give it a try. So can this quantity be equal to 0? How would you try to answer this question? All right. It cannot be equal to 0. I mostly agree with that statement. So can you give me the reason why it cannot be equal to 0?
U is a function of z.
U is a function of z, correct?
I is equal to constant.
They are constant, right? But a function could be equal to a constant, a particular value at some point, right? For example, if this is equal to 2 and u is also equal to 2 at a single point, then the difference is equal to 0, right? And if the difference is equal to 0, then the whole thing again dies. And we lose the second derivative, which is the highest derivative. And that's a problem, because if we lose the second derivative, we will lose the opportunity to specifying boundary conditions, because boundary conditions can only exist if we have derivatives. If the boundary condition, if a derivative is not there, boundary conditions are not necessary. You will not be able to solve the problem. Essentially, what will happen that you will have more equations than unknowns if second derivative disappears. Okay? So,
We got this one.
all right, that's what we need to look at. Whether this is real or complex, because if one thing is real, the other one is complex, no matter what you do with them, add them or subtract them, they will not be able to give you zero, because real and imaginary parts both have to cancel, right? So U is defined as a real physical quantity. Sigma does contain real and imaginary part. And which one will be a savior, real or imaginary part? If we're talking about sigma, which one will prevent this whole thing to become zero? Real part of sigma, sigma r, or sigma I? Which one?
Yep, real one.
Sigma r, right? Because sigma r multiplied by I will give you pure complex quantity, and U does not have any complex quantity, any imaginary part, right? So therefore, sigma r multiplied by I divided by alpha, no matter what, it will survive, provided that sigma r is not equal to zero, right? And what is the condition for sigma r being equal to zero? What does it define? If sigma r, remember, sigma r is the growth rate. Sigma r is negative, die. Sigma r is positive, grow. Sigma r is zero, what is that? Does not grow, does not decay, just neutral, right? So it is called neutral stability. So except for one point, everywhere else we are fine. Okay? So, but what we are actually interested in here is the case of instability or stability. So therefore, sigma equals zero, sigma r is equal to zero. It's not really of our interest. And for the case when, for example, if we're looking for unstable solutions, so we can exclude them. So we know that sigma r must be positive. So therefore, in that case, if sigma r is positive, this factor here is guaranteed not zero. If it is not zero, we can divide by that. And if we do, we will get, so the equivalent form of the same equation, just rewritten slightly differently, and it is rewritten like that: d squared phi, oh, sorry, not phi, psi hat. So you'll see that the notation I used in my handwritten notes are slightly different to what I have here. So what I do here on the board is more consistent, but these were written some time ago and I just didn't have time to correct them. So, but it is quite clear what I'm doing, so you will see. D squared psi hat minus alpha squared psi hat minus d squared u bar divided by u bar minus I sigma divided by alpha multiplied by psi hat, and that is to be equal to zero. So that's what it is. So further analysis will be concerned with the trying to see what this can produce, this equation can produce. And it will lead us to two physical conclusions. One is was introduced well, more than 150, well, 140 years, 145 years ago by Rayleigh himself. And the other one was introduced in 1970. It took 90 years for people to go from working on with the same equation from one statement, original statement, to the next. So that gives you an idea how slow the progress is and how clever we are, because we are covering that in a matter of just 1 hour, right? So that's how what progress, scientific progress does. So 100 years ago, it took us 90 years to do things. Now we can just routinely do that within 1 hour. So it's quite amazing. So, all right, what I will try to do is to multiply this whole equation by something. And because right-hand side is equal to 0, it will still be 0, right? So multiply the 0 by anything, it is still 0. So what I will do, I will multiply this by phi star. And phi star is complex conjugate. So unfortunate notation, a conflict of notation is that very frequently bar denotes complex conjugate. So, but here bar denotes the base flow, and it is completely real, so therefore it does not really matter whether it is bar or not, so it is still real, it's the same thing. So therefore don't get confused. But just for us to avoid this confusion further down the track, I will use star instead of over bar. Okay, so this is complex conjugate. So, and if I multiply this by star, phi star, and I multiply this by star, what will happen with this combination? What does it actually equal to? It is product between the complex value, function, complex valued function, and its complex conjugate. What do you get as a result?
It's likely to plot this.
You will get magnitude of this thing squared. And the important thing is that this is, of course, real. The number is complex, but its magnitude is real. It is computed using Pythagoras theorem. So real part squared plus imaginary part squared, square root of that. So you, of course, all know that. So just from basic theory of complex variables. So therefore, this will become a real quantity, and this will become also a real quantity. And importantly, it is not only real, but what do you think the magnitude is? What can you say about it? It is real and magnitude, and it is a even squared magnitude, so positive. So therefore, this is to be positive. So this is positive, this is positive, multiplied by alpha squared. Alpha squared is definitely positive, so this whole thing is positive. This thing here, well, we don't know, because this might be positive, might be negative, and this could be also even positive, negative. Well, not, it could be, this quantity here is, moreover, it is actually complex, right? Complex valued. So, and the question is what that is, right? So, and this, we cannot say that it is real at this stage, because these are different functions, complex conjugate of a function and second derivative of a function. So the product could be anything, because they are completely different functions in general. Okay. Let me now do the following. I integrate this between the plates. Okay? So if I integrate this between the plates, then the right-hand side will be what? If I integrate between two limits. It's not an indefinite integral. I'm talking about integral between z equals minus 1/2 to z equals 1/2. So what will happen? Integrate 0 between two limits. What do you get as a result? Okay, that's what I call trivial question, because it assumes trivial answer and everyone gets confused because it is too trivial. So what is the definite integral of 0? 0, of course, because definite integral is area. What is area of 0 height? Well, it's just a line, it doesn't have area, so it is 0. So even if I integrate it, I will still get 0 on the right-hand side. So let me try to do this term by term. So psi d squared psi hat star minus 1/2 and 1/2. multiplied by dz. Okay, integrate between over the gap. So when we integrate the product, what is the commonly used integration rule?
Why?
By parts, of course. Yes. So we have derivative, we have a function, and the integration in that case would be rather simple. Of course, evaluated between -1/2 and 1/2, and minus the integral between -1/2 and 1/2 over psi complex conjugate d psi hat dz. Right? So what is this equal to? This bit here. 0, because psi is equal to 0 at the ends. 0 is a real number, so complex conjugate of a real number is the same. So 0 becomes remains 0. So therefore, this is going to die. This is 0. And what about this one? So we cannot get rid of the integral. But it is complex conjugate of a function multiplied by a function. Doesn't matter that these are actually derivative functions, but these are the same functions. So one is complex conjugate over the other. So therefore, that is, oh, not that. Agree? That's what that is. So it is just the square root of a positive quantity. Why positive? Because, well, we don't care that it is derivative, but it is magnitude of derivative. And it is squared, so therefore it is real and it is positive. So integral of a real and positive function will necessarily be area, which is positive, right? But there is a minus sign in front of it, right? So therefore, this is negatively defined result. So this will necessarily produce the negative outcome, right? So this is definitely negative. All right. So what's next? So now I combine this result with integration of the second part, and if I do that, I will get integral from -1/2 to 1/2 of, so I'll use that result, d psi hat squared plus alpha squared psi magnitude squared dz. And so note that this is minus and there is a minus there, and I did not write it because I also have minus here, so I'll just make it plus. So I don't like minuses floating around because they get lost. So I'd rather get rid of them from the very beginning. So plus integral d squared u bar divided by u bar minus I sigma over alpha psi hat magnitude squared dz, right? And the right hand side was 0 and it is still 0. Right. So let's look at this. So we already know that this is positively defined, but more importantly, it is real. Agree? It is real. Now let's look at this one. So clearly this is real. This is real as well. So is this. Sigma is not. Sigma in general contains real and imaginary part, and if you take imaginary part and multiply it by I, you will get a real quantity. But if you take sigma, real part of sigma, and multiply it by I, you will get complex quantity, like imaginary quantity. So therefore, this is definitely real, but this one is definitely complex. So how can we add two numbers, which one of which is complex, one of which is definitely real, and get definite zero? We must have zero. Well, how? So real parts might balance each other and kill each other, right? Cancel each other. But because imaginary part only present in one of the expressions, so that imaginary part must be equal to zero, right? So this integral must integrate in such a way that imaginary part of the expression, final expression, vanish. It must. Okay, so I'll just, for my own reference, I write that sigma r plus I sigma I, that's what my sigma is. And therefore this expression here is going to be complex valued, and imaginary part is not balanced by anything, so it must vanish on its own. Okay, so let us focus on this expression. And to do that, I need some real estate, so I will create an extra slide. So let me consider this term, d squared u bar divided by u bar minus I sigma r plus I sigma I. So I just show it in explicit form, divided by alpha, and this whole thing is multiplied by psi hat magnitude squared. So what we really need to do is to split real and imaginary parts. And of course, the way we do that, we multiply the denominator, which contains complex quantity, by complex conjugate of the denominator. Then we will get real magnitude in the denominator. But if we multiply denominator, we have to multiply the numerator as well. And therefore, we will get d squared u bar multiplied by psi hat magnitude squared divided by u bar minus I sigma r minus sigma I. Okay, so that's this divided by alpha magnitude of that squared and multiplied by u bar plus, so pretty much plus I sigma r minus sigma I divided by alpha. Okay. Please check. Okay, it's late in the day, so even though I had some rest, so keep checking me. Does everyone agree with what I have written? Oh, good. Okay. Okay. Do I agree with myself? So it is. So it should be. Yeah. Okay. So see, I told you. So All right. So, and now we can clearly see that imaginary part comes from here. And real part, well, the rest of it is real part. So, but imaginary part is here because this thing here, this now is definitely real. And this is positive, and this is positive. This could be positive, negative, whatever. But this is definitely the only contribution which will come from here, will come, so complex contribution will come from this term alone, nothing else. So, consider imaginary part. So consider only imaginary part. So, which means u is not there, sigma I is not there, sigma r is there. So therefore it will be sigma r divided by alpha multiplied by the integral. Remember, this is part of the integration, so it is minus 1/2 and 1/2, right, of d squared u bar psi hat magnitude divided by u bar minus well, look, I will just write it as sigma back, so I don't really care about this structure anymore. So, and that will be magnitude squared of that dz. Okay? So that is, well, remember, just recollect where it comes from. We are trying to look at this integral here, and we're taking the imaginary part out of it because it cannot be balanced by the other terms. So therefore it has to be 0 on its own. Agree? So that's the logic here. And that's how it will look. So sigma r, if it is stable or unstable, it is not 0. So therefore if sigma r is equal to 0, of course it disappears, but that creates a sort of trivial case. We consider sigma r either positive or negative, so therefore this factor here is never 0. Okay? So therefore, this thing on its own must be 0. Can this be 0? No, because if this is, that's the magnitude, right? If the magnitude is equal to 0, it means that the function itself must be equal to 0. If it is 0, then there are no perturbations, right? So that's unphysical. All right, so this is not 0. What about this one? No, we discussed that it cannot be equal to 0. After all, it is in the denominator. So it's definitely positive as well. So therefore, this bit here is definitely positive. If the whole thing, if this is also positive, what will happen? Well, the integral of a positive function is going to be positive. We need to make it 0. All right, what if this is only, or can only be negative? So this is still positive, this is only negative, so therefore the whole thing is negative, right? So if it is negative, integral of a negative function is negative, non-zero. So from here we conclude that the only way we can satisfy the condition would be by requiring that this quantity, which is a second derivative of the base flow, has to change sign. Somewhere it has to be positive, somewhere it has to be negative. Only in this case we can balance the equation. Only in this case we can get the integral which is equal to 0. So, conclusion. D squared u bar must change sign somewhere between the plates. Somewhere it has to change the sign. If it does not change the sign, we cannot balance the equation. Okay? So,
there's a bit still the sign somewhere else just between two symmetric points.
Somewhere in the domain between. So somewhere in the domain. So basically, the sketch should look like that. So if we have, say, z and u as a function. So this is my left or bottom plate minus 1/2. This is my right or top plate 1/2. So there is some sort of distribution here, right? So, and that distribution here must have second derivative changing sign, right? Somewhere inside, right? Not necessarily at the boundaries, and most likely not at the boundaries, but somewhere inside. So that's why I put this not equal sign, but strictly side. So it is inside. Because it is on the boundary, it doesn't help. Because at the boundary, it's a single point and the rest of it is either positive or negative, so it's not going to work. So it has to be somewhere in the middle, in the bulk. All right, so if we have a function, and the function has its derivative, second derivative, that changes sign. What does second derivative represent? It's a curvature, right? And what does positive curvature mean? How does it look? So, do you know the rain rule? Have you ever been taught that? So, it's just mnemonic rule, which it will accumulate. There was no water, and then there will be water there. So, positive. So, this is positive curvature, right? It is concave. And if it rains and you stretch your hand like that, water will not be there. And if there was some water here, it will just run away. Okay? So, was water there? No water there. So, the process, well, essentially the amount of water becomes, well, it decreases. So it's negative, right? So this is negative curvature. Positive, negative. So somewhere in the domain, we should have positive curvature and negative curvature. And somewhere, curvature will have to change from positive to negative. And this point here is called inflection point. So therefore, this is a famous result by Rayleigh, who stated that if we want to have non-observable flow, so some sort of unstable flow, then we must have inflection point inside. Okay? If inflection point is not present, then perturbations are necessarily such that psi itself is equal to 0, so perturbations are not existent, so the flow remains stable. So this is necessary condition for instability. Okay? If this condition is not satisfied, well, be happy, what you consider will be physically observable. Okay? The base flow you choose is actually stable and you can work with it. So from here we conclude that the whole class of functions which do not have this would be physically observable. If you have something like that, then I will be careful here. Chances are that that will not be observable. That was the result, famous Rayleigh's result, so-called inflection point instability, it is called. And a lot of physical flows, they actually follow this rule. A lot of them. Right now, we are still working with idealized inviscid flows, and therefore I will show you some examples, but they were sort of very simple illustrative examples, not really physical examples. But later on, we will be dealing with situations where the flows will include viscosity, and they will follow this rule of instability by Rayleigh. Okay, so here we go. So Rayleigh's instability criterion, you must have inflection point. So this result, as I mentioned to you, stood for 90 years. Unchallenged, unchanged, until a guy with a strange name, Fjortoft. And this is Scandinavian name. So I'm not sure if, I think he was either Norwegian or Swedish. I don't remember exactly who his origin, so I can look it up. But he actually made the next step. So going through all this, so he did not challenge any of that, of course. It was very well established by then. But what he said, well, look, what we're focused on here is analysis of imaginary part. But what about real part? We know that it has to be balanced, and it has a chance of being balanced, right? So two terms might always cancel each other. But he was more careful here. Well, really? Well, two terms can cancel each other. So one is 2, one is -2, yeah. But what if one is 2 and the other one is -1? In that case, there is no balance, right? So therefore, we have to examine what happens with the real part more closely. And that's what he has done. So I will go to the next topic, which leads us to Fjortoft's theorem. So okay, so where to from here? So I will now go make a step back. So this is what we considered. So this is complex. Okay, so that's what we discussed. And that's the only part which contains imaginary part, so it has to be 0 on its own, and that leads to the condition that we will have to have the inflection point. But now let's consider real part. So real part will consist of this whole integral and something coming from here. Okay? So we have this d squared u bar multiplied by squared divided by u minus I sigma I, oh, sorry, sigma I. As sigma over alpha magnitude of that squared multiplied by u bar plus sigma I divided by alpha dz. So where does that come from? Just to remind you, this term here, right? So that's the same expression as I just wrote it there. And before we considered sigma r, now we consider sigma I from the same expression, right? Because that will be real. So that's this. And of course, we have plus the integral which was always there, minus 1/2 And that was the psi hat squared plus alpha squared psi magnitude of that squared dz. Okay, and this is equal to 0. So that's what we have. So the only thing is that I swap them. So, and I will also do another cosmetic thing. So what I will do, I will simply put equal sign here and minus here, and I will get rid of this, right? And the reason for that is simple, because this is sign-defined function. So it is positive, right? Integral of a positive function is positive. There is a minus sign in front of it, so this is definitely negative. Okay? So that means that this whole thing must integrate to give me negative quantity. Okay? That's what that means. So, in order for this whole thing to produce a negative quantity, what should I require? So, which parts of this integral can actually be made negative so that the integral also becomes negative?
You got this.
So this is definitely positive. We cannot change it. We cannot make it negative. And this one cannot be made negative. So the only thing that we can make negative is the product of the second derivative and this whole bracket, right? That's the only thing which can become negative. Okay. But let me go back. This thing here, what is it equal to? Remember, this is imaginary part, and it is not balanced by anything. So therefore, this whole thing has to be equal to what? 0. So, okay, so let me just modify this. So instead of having this follow sign, I will write that this is 0, and therefore, like that. So this whole thing, this whole expression integrates to 0. It got to integrate to 0, otherwise we are in trouble. Well, 0 has a very nice property. You multiply it by anything, it is still 0. Or if you change, if you add 0 to anything else, nothing will change. And we will play this game here. So how? I will play this game by... So whenever I touch the board with anything, it creates like a mark. So, all right. So let's see what the game is. So I will write the same integral from -1/2 to 1/2, and I will get d squared u bar divided by u minus I sigma over alpha squared psi magnitude squared, okay, multiplied by u bar plus sigma I over alpha. So it's essentially copy and paste of what I had before. And then I will add, so that's a witchcraft, algebraic witchcraft, and I will add the integral minus 1/2 to 1/2 of d squared u, what is that? U bar this thing squared divided by u minus I sigma over alpha magnitude squared dz. Did I change anything? No, because this is 0. We know that this is 0, so I subtracted 0, so nothing has changed. All right, so you might be thinking that I'm crazy just doing these things, but I'm just following somebody else's footsteps. So somebody else was crazy enough to come up with this. So, and I will also do the following. Sigma I divided by alpha plus u sub s. So I will tell you what u sub s is. So for the time being, I just take this integral, which I know is 0, and I multiply it by this combination. What sigma I is constant. Alpha is constant, so therefore this is a constant. And this is just another constant, which I have not decided yet on. So this is constant, the whole bracket is constant. It is multiplied by 0. It still does not change anything. But by now you can see what I'm going to do. So I'm going to combine these two integrals. And it is clear why I'm doing that, because this bit here will cancel, right? So this also is constant, and it will cancel with this one. So therefore, this result is going to look like minus 1/2 to 1/2 d squared u bar divided by u minus I sigma alpha squared psi hat squared, and I will have u bar minus u s dz, right? So because these terms will cancel out, but this will be introduced instead. So far so good. And now I define u sub s. U sub s is equal to u, which is a base flow value at point z sub s. Okay, so you're still probably thinking that I'm going crazy because I don't know what u of s is, and now I say that it is some function of unknown quantity z of s. So, all right, but I'm getting to where I want to be. So, and now I define z of s. Z of s is such that u bar double prime, or rather d squared u z of s is equal to 0. Now it becomes clear what I actually mean. So second derivative at a point is equal to 0, which means that point is what? That's where the curvature changes from positive to negative or from negative to positive. It is inflection point. And the meaning of this u sub s is the velocity, base flow velocity at inflection point, which is again a measurable quantity. It's not something we need to compute, right? For example, that's definitely something which is much better compared to sigma I, because sigma I, we don't know what it is. And sigma I, apparently we don't need it. But this quantity here is measurable. All you need to do is to look at the profile, at the velocity profile, which is, we assume it is known, and then we just tell what the numerical value of that is straight away. So therefore, this is not a problem. Okay. So remember that this whole thing, it's essentially the left-hand side of that expression over there. And it has to be negative. So what does that mean? Well, this is still positive. This is still positive. And our equation on our condition reduces to the fact that the derivative, second derivative of a base flow profile, which we should know, we know, right? So because we assume that U bar is known, multiplied by the difference between the value at the inflection point, which we also know, and local velocity, which we also know, it must be what? Negative. Because if it is not negative, it is impossible to make the whole integral negative. So therefore, d squared u bar minus u sub s must be negative somewhere between -1/2 and 1/2. So it's not only the second derivative which has to be 0 somewhere, but this combination here has to be negative somewhere. Only in that case we will be able to say that the flow might be unstable. Otherwise, if these conditions, two conditions, are not satisfied, then we are happy because our flow, base flow, is stable. Nothing will go wrong with it. We will be able to see that. It's only these two conditions that we need to keep checking, because they might tell us that something bad is happening with the base flow. All right. So this is Rayleigh. So there is a point where the second derivative of the base flow is 0, and this is Fjortoft. Two conditions. If at least one of these conditions is not satisfied, then instability cannot set. Okay? So what is left for us for today, what I planned for today? So what I planned for today is to spend a few minutes just to show you examples where these lead to stability or instability. And after that, actually consider a profile, specific base flow profile, for which I will ask you to compute all the solutions. I will lead you through, but you will be actually doing the algebra. And that is what you should expect in the final test. So obviously I will be mindful of the time that you will have there, so it will not be as lengthy as what we will be going through in the last hour today. But that's basically the plan for today. All right. So I'll just create a new page and draw a few pictures. And after the break, we will discuss which one of them could and could not be stable. Okay. So I'm not going to say anything until the end of this session anyway, so you might leave. I just will draw a few pictures here. So It's up to you. So if you want to go for and have some copper over there, go ahead.
Genau. Ja, der.